We're recording.
So we'll get started with the presentations in just a second. A couple notes. So many of the projects being presented are open for collaboration. This is the Open Collab meeting after all. Speakers, please mention at the beginning or the end of your talk whether you're actually open to being contacted about ideas with feedback or with thoughts or anything. And make sure that you've included your contact information somewhere on your slides. Our presentation format today will be 6 minutes each. We have a few less people than last time, so we have a little bit more time. So 6 minutes each. At 5 minutes, 30 seconds, we'll draw 30 seconds on the screen and everyone will see it, so you'll know you should start to wrap up. We'll also have time for roughly 1 minute of questions after each speaker. Feel free to post questions in the chat if you're watching and you have a question in the middle of the talk. Just paste it in the chat if you'd like, and then we can get to that afterward. Whoever is up next after each speaker should get ready so that we can kind of quickly switch and minimize downtime. And after this whole hour, so we'll go until 4:55 or so Pacific, so 55 minutes later, we're all going to move over to Discord. And in Discord, there's one voice channel per speaker. So if you want to have a more in-depth conversation with the speaker about anything that they presented, just go hang out on Discord and you can chat as long as you'd like. No time pressure. All right, I think we should just get started. Oh, one more thing. The next research jam will be in 9 weeks, August 4th. It's already on the website. It's kind of a week and a half after ICML ends. So if you're excited about something here today, you want to work on something and show up for the next one and present, you have 9 weeks to make some progress. All right, so let's start. The list of speakers is on the website, and the first one is Nick Doiron?
I say Doran, but right? Yes, you're very close.
Okay, perfect. Well, you're up first. Feel free to share screen and get started.
All right, let me do that. All right, so I'm going to be talking about GPT-NYC, which I believe is the first city-specific language generation model. If you know of another one, let me know. For now, I say a city-specific one. And that's my Twitter and GitHub username if you want to contact me there. Just like quick 30 seconds for people who are not familiar with natural language processing and language models. Currently, the way that usually works is there's a huge amount of unorganized text in English or another language. You do the pre-training, that gets you something like GPT-2, and then you fine-tune it on a specific task. In this case, it's going to be information about New York City. And there are several different language models with different architectures. BERT is one that fills in words and be used for different tasks. Sequence to sequence, usually used for translating. And the GPT, which is what this is based on, is you have a string of words to kind of prompt the language model, and then it just starts rambling as long as it wants to go until it reaches the end of the text or you tell it to stop writing. So several people use it for like creative writing things. So I've decided to fine tune it on questions and answers from a subreddit called Ask NYC. In 2012, it split off from the other two New York City subreddits. There's a whole other drama about why are there two separate New York subreddits, but there's a third one that is just for beginner questions like I'm moving to New York or I'm visiting New York, where do I get this kind of food? Or what does a local person think I should do? And I know that Reddit is sort of a troublesome place to get content, so I've filtered by number. There should be upvotes on this, and it should be a direct response to the question. And in order to train or fine-tune the model, I've formatted each one of the question, additional description, and then responses with this kind of key format where there's a hyphen and then there's a %%, because it's unlikely someone would write %% in the middle of natural text. So there's like a division between I'm prompting the question or I'm prompting something, and then now you're going to respond to the prompt. A word about vocabulary. So all these different language models have their own vocab.txt or vocab.json of words that they recognize and transform into a token in their model embedding space. And I looked up what are the most common words on Ask NYC using kind of like a naive tokenization thing that are not in the GPT-2 vocabulary. Like, are they essential? Do I need to add more tokens? And this is a sample of them, touristy, gentrified, different neighborhood names. A lot of foods, I was surprised, are not their own token in GPT-2, like bagel, dumpling, a burrito. Stroller is an interesting one because, like, you know, for a parent's perspective, you're asking, like, can I take my stroller on the bus or something? Um, and I decided to add a lot of these words and then also neighborhoods, names of subway stations. I found a list of like 100 foods to try before you die and add them as tokens. Um, Now, just because something isn't a token doesn't mean the model doesn't know what it is. Like, it can memorize names and kind of spit them back out at you. But I think that there's some information loss if you know, doesn't really know what a bodega or a deli is, or it just kind of splits that up into different consonants. So I don't have like proof of this, but I felt like adding New York specific vocabulary would make it a more New York feeling language model. Got this. So initially, when I tried it out, I had a few problems before I came up with that special formatting for question and answer. Sometimes on the lower one is actually this example, it would fill in like what it thought the rest of the question should be. Like I said, visiting New York for 1 week, and it said, "Oh, hi guys, my wife and I are coming to New York City for 1 week." Like invented this question, and that's not what I wanted it to do. I want it to answer or give ideas. The one on the top one is interesting because this is with the GPT, the smaller model, like GPT-2 small. Uh, it's interesting because it says, "Oh, the train's horrible. Get into this train at LGA, gets you to JFK Airport, can be delayed. Go to Times Square, take the E into Williamsburg." It sounds like someone is giving you directions, but these are all nonsensical. Like they're not factual directions. If you've ever been to New York, it sounds like someone's giving you directions, and then you're like, "Wait, there's no way I could get that train from that place to that." It's just as if you didn't know what these actually meant. So I thought it was interesting. Like it sounds like a response, but it is not a valid response. So I trained on the larger model and used this kind of percent thing to separate out question and answers. And I really like some of these answers. I said, "Is Bushwick good for families?" And someone responded, "Family friendly." I said, "How often do you go to Central Park?" It gave a reasonable answer. I asked, "How do I get to Governor's Island?" And it came up with this URL. And so this is something that's kind of interesting is GPT is known to memorize certain sequences in its training or fine tuning data. And this is like the answer. Like if you were going to give like a one line answer to how do I get to Governor's Island, this park in New York, you want to go to this link. Um, and so to better understand how that link came out, like it's not like super smart. It didn't like read what's on that page. Instead, like it's memorized that. And we can see that if you look at, there's a package called Echo, ECCO, which tells you the probability of the next token. And you can see once you choose the top token, HTTPS, is very likely you're going to fill in the rest of the tokens of that URL. I have only 30 seconds, so say there's some constructed answers where you ask a question that doesn't have a definitive answer, and it starts kind of writing some different creative writing prompts. But none of these are like valid answers. They're sort of starting like an answer, but none of these places are real places that exist. And then thinking about toxicity, obviously there's not enough time. This could be a whole research project in itself. I'm looking up 2 different papers, reading toxicity prompts and probing toxic content to think about how can I make sure that the model is not offending people when it answers questions about New York, because there's a lot of content both in the training data and in what people are going to ask. In the future, I'd like to train on other models, Hawaii visitors, Japan travel, or similar subreddits. Thanks. And I'm looking for a machine learning engineering job. I don't know if we're allowed to promote ourselves a little bit, but that's the thing.
That's fine. That's pretty cool. Did that URL work?
Yeah, that's definitely the New York Parks URL where you would go and it would tell you about how to get to Governor's Island.
That's awesome. That's awesome. We're right about at 7 minutes, so we should move on with the next speaker. But thanks, Nick. And if you have more questions for Nick, please show up in the Discord afterward. Next up, we have Alex Shim, giving us a probabilistic interpretation of transformers. Take it away.
All right, so I'm Alex Shim. This is my work about a probabilistic interpretation of transformers. Now, as we all know, transformers have reached state of the art. And there's actually some computationally cheaper alternatives to transformers. And it turns out that it seems like an upper bound on the performance is actually the standard exponential dot product attention. And the question is, why is this the case? Is there something inherently special about it? And this paper is sort of trying to explore why that is the case. And to do that, we're going to look into the statistical concept of exponential families, which can all be written in this form over here. And the key characteristic is this: it's proportional to this e to the u of x, which is the sufficient statistic dot product with the natural parameter eta. And there is an important concept which will reoccur, which is called a normalization constant, which is an integration of this unnormalized probability over the entire state space. And for this intrinsic measure h of x, there's a particular case where if we have a large sample space, but if we restrict it to a finite set of points, we can actually define h of x to be 1 for those points and 0 otherwise. And this actually makes our integration into a summation. And we see in this form that the contrastive probability, if we set the natural parameter to be the query and the sufficient statistic to be one of the keys, it's actually exactly the form of an exponential family. And importantly, there's a special property of exponential families where the gradient of the log normalizer is equal to the expected sufficient statistic. And if we think about what a discrete exponential family is, since now this attention is actually a exponential family probability distribution, what we're actually saying is that this attention sublayer is actually the gradient of the log normalizer. So it's actually performing a gradient update step on the log normalizer function. Now, there's an interesting question: why do we want to optimize a log normalizer in the first place? Now, in this discrete case, there's actually, this occurs in convex optimization, and it's called the log sum of exponents, and it can be solved by using Lagrange multipliers, which interestingly enough converts it into the maximum entropy problem. And this brings us into a lot of ideas in information theory and KL divergence. And if we use Boltzmann distributions, we can extend this to continuous distributions, and we basically get statistical mechanics. And Jaynes's maximum entropy works off of the log normalizer. Boosting, Shapiro's interpretation of boosting works as well as variational inference evidence all around. Now, what are the shortcomings of this? I know I'm going pretty fast, but one is that we are actually performing n parallel gradient update steps for each hidden state. And so we could sort of view our hidden state as a discrete distribution. And now one idea which might help us is that for statistical inference for temporal models, there's something called particle filtering where you're trying to estimate updates on the marginal distribution at each time step, and you're using samples to do so. And one particular case is if our temporal model is based off of a mixture distribution, which is a mixture of discrete and continuous random variables. And we could start with n mixtures, but because of our discrete update, each discrete updates will blow it up by multiplied times n. So we end up with n squared mixtures at the second time step and n cubed at the third time step. So this means we'll have exponential blowups. So in order to attractively handle this, we do what's called approximate inference, where we collapse the n squared mixtures back down to n mixtures. And in particular, so once again, we're starting with n samples or a mixture of n distributions. And if we choose for our transition our exponential family distribution, what we're actually doing is we're creating a distribution of our natural parameter space. And now if we marginalize over the natural parameters and we calculate the sufficient statistic, and we collapse the sufficient statistic over a mixture, we get something which is once again the attention function. And in particular, one note is that we can use other kernels, and this sort of works. Basically, this is the essence of graph neural network attention updates, in my opinion, because your message passing is actually calculating a sufficient statistic. In summary, exponential dot product attention can be viewed as an exponential family distribution. It's actually equivalent to the Hopfield network. The loss has a free energy and maximum entropy interpretation, and one idea is that we can use sequential Monte Carlo to interpret the hidden states as a propagation of samples over time. Okay.
That was very fast.
Oh.
We're only at 4:15. Anyone have any questions? Feel free to just ask. We have a couple minutes.
I went probably faster. I mean, there's a lot more, but I can.
Sure, I have a question.
Sure.
So typically in Hopfield networks, they're trained with Hebbian learning, but obviously these things are, they're not trained with Hebbian learning. So can you just clarify what you mean by the gradient descent interpretation?
So basically, both the Hopfield networks have an energy function, and the energy function is actually equivalent to the log normalizer of an exponential family distribution. And what they do is they update the Hopfield energy function with what's a sort of gradient update.
But the Hopfield energy is at 0 temperature.
I'm not sure about this, or I can't comment on this. I'd have to think about it more.
That's fine. Maybe it's a generalized Hopfield. There may be there are temperature dependent variants. I'm an old man, so I remember all this stuff. So. But that's fine. So go ahead. You're saying it has a gradient descent interpretation.
Yeah. So basically, and there's actually a blog post which came with a similar conclusion, and I think all the math points out this way. So basically, you could, if you perform this, if you have this interpretation, you pretty much end up with a Hopfield energy. And if you actually look in the math behind Hopfield networks, they also talk about the LSE, the log sum of exponents function. And what they're really doing is, if you think about it, I actually asked Hopwriter this at like NeurIPS 2021, and I asked, if you think about a discrete interpretation, then like, okay, basically, can you see it as probability distribution? And of course, all the math is leading that way. And this convex optimization is for log sum of exponents is based off the idea that you're working with a multi-Newly distribution in the first place.
Okay.
This is like an alternative explanation, but equivalent explanation. And I don't know if it's better or not, because maybe you avoid the neuroscience ideas, but then you use statistical ideas instead.
Interesting. I think there could be a lot more deep conversation here. For timing, we should go on with the next presenter, but feel free to chat with Alex in the Discord afterward. Yep. Next up, we have Gaston.
Yeah.
Gaston.
Okay.
Feel free to share a screen when you're ready, and
okay. Hey, I'm gonna talk about AIfriendly.com. Okay, AIfriendly.com is a website. So let's move on. AIfriendly.com is a website that consists in the following dynamic for the users. Now, this is the user. It will provide 2 Excel files, Microsoft Excel files, to the website, which will answer back with another Excel file called the outcome. So this is a website done by the recently created, like 5 years ago, the International Center for Advanced Studies, which is related to the Center for Advanced Studies in Princeton and the University of Buenos Aires, which is the so-called the best, #1 university in Latin America for the career of Master in Physics. So let's please quickly explore the website. This is an example of a problem that can be tackled. This is a Microsoft Excel file which has so-called features in each column, and finally another column with a binary variable. So the website consists then with a binary network that has by default 2 dense layers of approximately 32 units by default, and as an output just 1 unit, which is the one that performs binary classification. So let's just cover its basic usage so I can explain why am I showing this here. Okay, yes. So first you provide the learn card, which is just in the website you upload the Excel file, which is like a training data set. No, it has the correct tags for the input variables. Then you provide the in card, which is an Excel file that does not have the tag for the correct answer. No, the website is going to predict over that data. And finally, you provide your email. So what will the website answer you back? Yes, first, you can perform some level of neural network customization. Some basic customizations, such as defining the amount of units per layer, then the activation function, then the number of epochs that is used for training, and there is so-called advanced customization that allows to change the optimizer, add extra features such as noise, process it with a Gaussian operation, then add take the sign of each feature, add quadratic interactions, make it convolutional as if the features were not independent features, but for example, you were dealing with a time series, then add another layer and change the activation functions, also change the batch size and the learning rate. So that is the possibility of, for free obviously, using a neural network online to predict over data. The results are sent by mail, that is the predictions over the so-called in-card, and you also have a link to a personal but public website that allows to see the so-called ROC curve, receiver operating characteristic, in Spanish, curva ROC, in English, I guess it's ROC. So you can also watch the accuracy as a function of the epochs and also the loss as a function of the epochs. So I'm bringing this project here, obviously, to tell you about it because it's fun, and I would also like to tell you that we are using this in the university as it's a very traditional career. Yeah, and physics has a great part of its curricula dates back to 1850, 1900, maybe 1920, the quantum revolution. So there is absolutely zero contact with machine learning in the career. We are adding this to the curricula, in particular during the COVID-19 pandemic, by adding this as a complement for the laboratories, now the physics laboratories. So we came up with a couple of examples for the pupils to learn during their career. For example, a case of detecting the creation and decay of Higgs bosons. Now this is the rosy curve of detecting the Higgs boson over particle simulations. Then there is this interesting case which can be actually done empirically, in an electronics laboratory. It's an amplifier circuit, and you can predict if the diode will burn as a function of the passive components. So these are only two examples. I would like just to thank you and tell you two things. Obviously, contributions are welcome at the repository. Basically, we are looking for binary classification examples to add into the physics curricula for people when people start the career to just be in contact and easily use a neural network. So we're open to two things. First, examples, and in the second place, just other courses also using this website. Now we're open for that too, and if you happen to use it in your teaching, in your classes, we would like just to be told so we can approximately configure how much computational resources are allocated to this server. So that's it. I would like to thank you for your time, and if you want to have examples, please reach out.
Awesome. Thanks for presenting. Anyone have any questions for Gaston?
So when you say you welcome contributions to the code base, do you mostly refer to the application problems, or can people just add, say, a third optimizer in addition to SGD and Atom, or like the core functionalities?
Great.
Can people do that?
Great point. Both things are very much welcome. Yes. The only constraint is that because of computational constraints, we cannot handle images as a data set of images, for convolutional two-dimensional operations or three-dimensional, But inside our computational capabilities, all type of contributions are very much welcome.
Any other questions?
Okay.
All right, great. Well, thank you. Thank you, Gaston. We'll continue with Fatima, who has already started sharing her screen. Perfect.
I'm here to explain my problem, image targeting using the style transfer models. So first, I need to create the introduction on what is image targeting. Image targeting is kind of image resizing, but considering the image content. The simplest way to do image targeting is image cropping, is the simplest operator. We are keeping the important part of the image and removing and cropping the unimportant part of that. And there are some other image targeting methods, and most of them are detection. I was working for Resident System Carving. Why image targeting exists? In case different size of and dimension of display exists, so image targeting exists. And it is a well-known important problem in computational photography. And is already implemented in Photoshop. Maybe some of you use it. Let's take a look at scene carving first. How it is working. Most of the image targeting method using a saliency map, and the simplest saliency map is creating using computing image energy. The lowest energy part are the uniform part and are an important part of the image, and the salience part of the important part. After computing the saliency map, so we can easily compute crop the keep the important part and crop down an important part, and or maybe do some another operation. And and some current models and some current method, and this model that you can see is about in painting is not our focus, but again another method that doing same thing like that, and considering the image content and not inputting another content on that are on focus. So let's take a look. What do we have? We have an image retargeting data set is on less than 100 sample, and you can see we have an input image and the output are retargeted size. What I'm thinking about is creating the same data set, a huge data set, and using the best model and maybe multi-models, and create this data set, and then apply SI transform this, maybe something like SI GAN, and consider the image dimension and image targeted image as a SI image. So our model can understand that it has a style, and so doing the image targeting as a style. And then maybe apply interface scan, and in case we train the model on an retargeted data sets, and there is some feature to understand the image dimension, I suppose, and I think maybe something like an interface scan that can understand the pose and age and expression, because there are data sets, because the model is trained on different, maybe different in pose cases. We have many faces in different pose, so the model can understand the pose. And in case our data set consists of many retargeted image, and so I would like, and I think the model can consider it as a parameter, so we can edit it dynamically. And that's all what I think. So in summary, we should create a data set and consider the model as consider it as a style transfer and apply a style GAN maybe, and then use interface scan and edit the latent space and create a optimal response. Thank you.
Thanks. Anyone have questions for Fatima? I can ask one. So can you say a little bit more, Fatima, about exactly how you would use GAN to do the retargeting?
I want to use it. It's not my purpose and what I'm
Okay, okay. How do you think it would work though? How do you imagine it would work?
I think it could work, especially in editing latent space, because when we train, by training a model, we created a latent space, and the features are going to sit in the latent space. And in case our data set, or new data sets, it consists of many features of multi-dimension of the same image. So I think the model should understand the dimension of the image, so we can change it then. And we can do that in this way. I should test it.
Okay, okay. So you would have explicit mappings. So here you have pose, age, expression, and so on. You would have your own explicit mappings for like X dimension and Y dimension, say.
Yeah, yes, exactly.
I see, I see. Okay. Anyone else have questions? We have another minute or so.
So there is this out-ish idea of spatial transformer. Seems like that would be perfect to solve this problem, but I guess people don't get it to work fully. Have you considered that?
I think if we consider it and create a data set perfectly, I think we can do something with that. I never tested. I need to test it. I was working on sim carving, and it's come in my mind in this. And currently, I was working on SI GAN, and I was thinking about how to mix them. And I think this is the way to do that.
All right, probably we should move on. Thanks, Fatima, for presenting. Next up, we have. Perfect. Yeah. Next up, we have Lucia giving an update on Project Escher. Lucia presented in the last research jam as well. Perfect. Works.
Cool. Round two. Nice.
Yes, I will give a brief introduction, and then I'll show some progress that we have made since last time. This is joint work with Simone Gaston as well, who spoke before, and Aditya Menon. So what we have, let me see if I can. Okay, from here. So this is the painting that we have. This is Escher's work called Print Gallery. And as you can see, the center is blank. For no reasons, he left the center blank and he put his signature on it. And our task is to fill in the center using machine learning. The tricky part is that this painting has a mathematical structure that we need to respect. And I will show you the mathematical structure that we have. And then we will use machine learning using the mathematical structure as a constraint. So that will be our guiding principle, let's say. It's machine learning for art reconstruction using a mathematical structure behind. So let's go into the math behind print gallery. This is a little bit quick depiction of what's going on. As you can see, there is a grid structure that is behind the painting. So you can superimpose this grid that it's kind of these squares. You can sense that the painting is kind of swirling in, or it's like a turning inside from outside in. So it's like a rope that, or a mesh that you're twisting inside. So to make this twisting effect, Escher used this very grid. And in particular, the painting has a repetition pattern. It's not very easy to see and to explain here quickly, but trust me that the painting, it's repeating itself. That's why it has like this looping effect and this twisting effect, that he wanted to create an infinite loop. So that's why he twisted the painting inside, and at some point, the painting repeats. Let me show you, if I have time. If I don't have time, doesn't matter. But this is a man looking at a boat. This is a small boat, if you see there. And this is the beginning of this gallery. You see here the arcs. Here's the entrance of a gallery. Here's another man, and here these arcs. And if you see, these arcs repeat here. Oops. So there is a repetition, and in a smaller scale. So what we did is, we said, okay, we need to continue this repetition, because what you have here is one arc, another arc that it's missing, and then it's blending in. He made this effect that it's blending in with these bigger arcs. So, okay, we have one arc that we need to continue, another arc that we need to continue, and then this blending pattern. So how do we do that? First, we know that there is a self-repeating, as we said, pattern going on. And this is exactly the repetition that it's inside. So if you zoom in the center, you see the repetition is not exactly repeated, but twisted. So it's repeated and twisted. And if you put it here in the center, you are left with all of this that it's blank. So we need to create content. In art, this is called, it's an expansion in the field of view. So basically, it's like you're zooming out. So you need, if you have zoom out, you're looking at a picture from afar, you need to create content that it's missing. In machine learning, this is called extrapolation. And basically, here we have like a sort of a ground truth of people who worked before. This was completed by hand. So it has some imperfections based on the model that they chose. And our idea is that machine learning will learn the Escher way of painting and the Escher way of painting in this painting. So it will be able to complete this part. Let me show you some results. We zoomed in, and we tried to complete this part of the buildings here. I don't know if how to zoom. I don't want to touch anything. Maybe I will close everything, but we try to create more buildings. You see that here there are more buildings, so we try to create more buildings. As you can see here that they created more buildings that they are expanding. So we use common guns, and the yellow part is the original, and this gray part is what we have created. You see that we need to match two things, the content and the twisting effect. So that's the creating content for a CNN or for image model is not so difficult, because there are many models that will extrapolate, but the difficult part is to learn the underlying math twisting that there is. So you can see we need to train our database better, because this is too modern. As you can see here, the buildings are just too modern. And so it's a matter of creating the right database for our problem, and then expanding much more, because we need to create more, and then creating a network that will learn the twisting or like end to end. It's content plus the you see that there is like a twisting effect, like it slides that we need. The network needs to create that sliding effect and it needs to continue. So extrapolating is a big issue in machine learning, and yeah, basically that's the path that we are in. We're not far, but yet training the database, yeah, it's actually something that it's laborious, that is task demanding, and then trying several models. This is called commod GANs, but we are trying on image GPT, and taming transformers are the other models that we are working with. So yeah, this is the progress that I think you haven't seen this nice building so far. Last time we created a building that had a graffiti on it because of the training database. So yeah, that was not good. I don't think it was on Escher's mind to put a building with a graffiti. So we're getting better, but we need to dedicate still some more time in the training database, and then selecting the model and selecting the loss. So
looks really good. It's
yeah, looks really
pretty
good
impressive generation. Yeah, I wonder if your graffiti is just modernizing Escher in a way that you would have liked anyway.
Yeah,
we're kind of out of time. We should move on just so we can get to Charles. But if people have thoughts, please meet Lucia in Discord. Charles.
Okay, great.
You're up next.
Can you hear me?
Yep.
Mm-hmm.
Okay, give me a second here to blow this up. See if you can see my screen. How many minutes do I have?
6. I'll drop
6 minutes.
30 seconds when you have 30 seconds, but yeah, 6 minutes.
Okay, can you see this?
Beautiful, yep.
Okay, so this is a talk about WeightWatcher. WeightWatcher is a open source tool that I've put together in collaboration with, well, this is based on research I'm doing in joint with Michael Mahoney. So this is this open source tool we've built, and what it is an implementation of our research into heavy-tailed self-regularization. So it's a Python open source tool. You can install it and run it. Let me give you an idea of what it does. The open source tool is called WeightWatcher. This is the GitHub page. It's an open source diagnostic tool for analyzing deep neural networks, and you do, without needing access to training or even test data. So it can be used to analyze pre-trained PyTorch and Keras models. So I'm continually adding versions, like we're going to add ON and X models this week. It allows you to inspect models that are difficult to train. It allows you to gauge improvements in model performance. So for example, you can predict test accuracies across different models as you vary hyperparameters. And again, you can do that without looking at the test data. And it allows you to detect potential problems that might arise when doing things like compressing or fine-tuning the models. So again, this is based on our theoretical work into why deep learning works. And it's based on ideas from random matrix theory, quantum statistical mechanics, and quantum statistical mechanics, and strongly correlated systems. And we have if you go to the GitHub page, we have a number of papers that we've published and talks. We have, for example, a paper coming out in Nature this year. We have one coming out, well, it's supposed to come, or hopefully it's still in press in JMLR, another that's been submitted to NeurEPS this year. So all this is published, but here I'm going to talk about the tool and what you can do with it. And again, this is an update from the last time. So the idea of the theory is that when you want to understand what causes generalization, traditional statistical learning theory would tell you that it's the scale of your weight matrices that cause generalization. That's why we regularize them. We regularize them to reduce their scale. You apply like an L2 regularization to try to prevent large elements from forming in the weight matrix. But regularization is not the same as generalization. And our theory, coming from physics, says that the generalization capacity of a neural network is really based on the shape, and it's based on the shape of the spectral density. So in other words, what the tool does is for each layer in your neural network, it will extract, plot, and fit the empirical spectral density, which is basically a histogram of the eigenvalues extracted for each layer weight matrix. And more importantly, the tail of this graph, so this right-hand part of the plot, this is on a log-log scale, the shape of the tail is that's what carries the most useful information. And so by looking at the tail of the spectral density, you can actually say something about generalization. So a lot of the theory is built around trying to analyze the tail of trained and pre-trained neural networks and seeing what we can learn. The way the tool works is very simple. You just import the tool. Import WeightWatcher is www. Create a tool, give it your model. You could say analyze, and you can, if you say plot equals true, it will generate a bunch of plots, and it will give you a details data frame. And this is what the data, it's just a pandas data frame with a bunch of metrics. A particular metric to pay attention to is alpha, because alpha is this metric I'm going to talk about. It's basically the slope of this line. Alpha is effectively the slope of this line. And you can get summary statistics. And the summary statistics are basically layer averages. So this alpha 3.06 is basically a naive average over all the layers. And so this is what the tool does. It generates a bunch of plots. And I'm going to talk about some of the things that we learned from the last talk we gave. And so one of the things that happened is, one of the things we think we can do with this alpha metric is that we can use it as a metric for early stopping. So our theory, the heavy-tailed self-regularization theory, suggests that when our power law metric alpha is less than 2, then your layers may be overtrained. And again, we're not looking at the test data. We're just saying, look at the weight matrix directly. Can we tell when a neural network is overtrained simply by looking at the weight matrix? That's what we're trying to do. And so we have this idea that if we take the layer average, that summary statistic, that when that's less than 2, that's when you should apply early stopping. So early stopping should be applied when the layer average is less than 2. So the last time I was here, I met a really smart guy named Xander Dunn, and he actually tried this. And so what he did is he built this big transformer model and he trained it till it was overtrained. So this is an example of the training loss. This is the validation loss, and this is the alpha. And what you found is as soon as the training loss kept going down, but as soon as the validation loss saturated and started going back up, alpha dropped below less than 2. So this was astounding because, I just told him to try it. He did it on his own, used the tool, found this out, showed it to me. And this is like a complete independent verification of the idea. So what we're doing right now is we're trying to set up a bunch of other models, and we're pursuing, in addition, like now that we have our latest NIPS paper submitted. And so this is one of the things we're looking at. This was extremely helpful to have access to this group because we found someone willing to use the tool, and we have a few other people now using the tool, testing this out. In fact, I could even say the tool is being used in a major hedge fund right now because they're attempting to do this. Another thing we are looking at is the notion of correlation traps. So this is another thing that's come up during the talk. So the idea is that we conjecture that when there are very, very large elements in W, so in other words, when the regularizer is not working, these act like correlation traps, and these can be seen in the log spectral plot of the weight matrices. And so you can apply the WeightWatcher tool, you can hit and randomize, and you can get these plots, and we believe this can be used to detect various forms of overfitting, once again, without looking at the weight matrices. So that's, we got some other stuff to talk about. That's basically the research update of where we are. You told me 30 seconds, is that right?
Yep.
Okay, so
Yep.
we have other results as well, but I'll stop there and let you ask questions.
That's really cool. A lot of people in chat think it's amazing results. I'll just ask one quickly, and then we should move on. But you say alpha becomes lower than 2. Is that for every layer simultaneously, or is that for a particular layer?
It's a good question. So we have the way I look at these models is that I look at them layer by layer. So I treat them as if I was analyzing each layer. I have a sort of an idea, like one layer might be overtrained and another layer might be over parameterized. So we have the idea that you can actually detect overtraining in a specific layer. But in the plots that Xander did here, he was looking at the layer averages.
Okay.
So he just looked across the entire system.
Perfect.
So you can do both.
Awesome. We just need to move on so we can end on time.
Got it.
So thanks for presenting, Andrew. If you're there,
yeah, I'm here.
To share screen and go for it.
For sure. Thanks, Jason.
Sorry to have to rush people along.
No worries. So you guys see my screen?
Yep.
Yes.
All right,
Perfect.
cool. So today I'll be talking about dissipative Hamiltonian neural networks, how to learn dissipative and conservative dynamics separately. So I actually did this with a member of the ML collective, Sam Graydonus. Me and Sam go way back. And so he wrote me into this project. It's super fun to do. And so essentially, change is the only constant in our world. And there are certain patterns to this change that take the form of conservation laws, conservation of mass, conservation of energy, conservation of momentum. And these conservation laws are present in many of the complex systems that we study, or that scientists study in general. So like molecular interactions, ocean currents, hurricanes, pollution, earthquakes, or even something as simple as a pendulum, as I have to the left right here. But how do we, I mean, us scientists, we struggle with modeling these very complex or even simple systems. And so I guess, you know, us computer scientists were like, oh, let's have a neural network try it. And so we threw a neural network at it. Previous work has done it, but not very well. And so essentially you had folks, I guess physicists figure out, yes, we can allow neural networks to model these super complex systems if we essentially give it a cheat code. If we embed the neural network with some type of physical knowledge. And this type of physical knowledge I'm talking about specifically is what we call physical priors. And so these physical processes are hard to model accurately with a regular neural net. And so to make it more accurate, we embed a physics prior into our network to make it more aware of how the real world works. And the prior in question for this project specifically is Hamiltonian mechanics. And Hamiltonian mechanics, in short, essentially just shows the time evolution of a dynamic system. In most cases, how energy, which is a conserved quantity, flows from one place to another. And so here, in this slide, we take data from a real, or I guess a simulated spring, and we replicate the conserved quantities. Well, our model extracts the conserved quantities and the dissipative quantities from the data. Because while, so scientists like to model systems, but they often model ideal systems. Like, for example, systems with no dissipative quantities. So no friction, no radiation, no heat transfer. But in the real world, things are not perfectly conserved. There's always some type of friction. There's always some type of energy that dissipates out of the system. And so we took a combination of ideas from physics, fluid dynamics, machine learning to be able to model real systems. So I mentioned that we use Hamiltonian mechanics, that's the physics part, as a physical prior to make our model smarter. But there's also another, I guess, critical thing to note is that any vector field and simple 2D physical systems can be represented as a vector field. So any vector field can be deconstructed into its conservative part and its dissipative part. Or rather, more accurately, its rotational part and irrotational part. And here we see the conservative field right here is very, I guess, rotational. And the irrotational part is essentially analogous to the dissipative quantities within a system. And so if we want to analyze conservative, I guess, conserved quantities within systems, we have to separate, at least in real systems, we have to separate the clean part from the messy part. And thus, this vector field can be deconstructed into its two component parts, a conservative part and a dissipative part. And so we embedded this knowledge, we embedded Hamiltonian mechanics and the concept of Helmholtz decompositions into a model. And so we observe a dynamic system, such as a spring. We take the states from the spring. So Q and P can be position and momentum, push it through a network or two subnetworks, a dissipative subnetwork and a Hamiltonian subnetwork. And we obtain the dissipative parts as well as the conservative parts. And so we essentially force the neural network model to learn both the conserved and the dissipative parts of the real system that we observe from data. And so we force it to learn it until we get the full system back. And so that's essentially what's happening here. And so this allows you, this technique actually allows you to do really cool things, to ask like, okay, so we observe a real system, but what if it had twice the amount of friction, or half the amount of friction, or 4 times the amount of friction? And so we get training data here. Oh, 30 seconds. Oh my gosh. Okay. Anyway, so you can modify the systems once you learn, I guess, the individual, each component part, the conservative part and dissipative part. So not to rush myself, we tested this on a pendulum, on a real damped pendulum, got some really good results with our model, especially against regular MLPs and Hamiltonian neural networks, which is the predecessor to our model. And we also tested on real ocean current data, which is probably most exciting.
This is super cool. I really hate to do this, but we have to go because we're actually using the Zoom from another organization so that we could have enough people, and they need to use Zoom for something else right now. Really sorry. This is amazing work. I love the original paper, and this seems cool. Let's all go to Discord. Can anyone paste the chat link to Discord?
Right.
Yeah, we'll have Discord for however long you want. So you can also share screen.
Yeah,
you can
let's
also
just
share
thank all the
screen
speakers super quickly. Thanks everyone. Amazing presentations. And we'll see you all on Discord right now. There's the link, or the link is also on the MLC Open Collab page.
Thank you. Bye.
All right. See ya.
Bye.
Thank you. See ya.